Welcome to All Things Photonics, a podcast about the physical science of light driving scientific innovation in the 21st century. I'm Joel Williams, Associate Editor at Photonics Media. Join us as we explore the latest trends in optics, lasers, microscopy, and spectroscopy. Each episode, you'll hear from leading voices from across the photonics landscape, brought to you by Photonics Media. Recent breakthroughs in quantum-integrated photonics, and those still looming on the horizon, are the things of Nobel Prize science. The incorporation of photons into the disciplines of quantum computing, quantum key distribution, and quantum metrology in particular, presents both obvious and more detailed advantages over bulk optics. The field also has an impressive roster of rising luminaries championing progress. Dirk England, Marcelo Davanco, Ali Ashari, and others come to mind. Matthew Eichenfield, the SPIE Endowed Chair in Optical Sciences and Associate Professor of Optical Sciences at the University of Arizona's Wyant College of, you guessed it, Optical Sciences, is a member of the aforementioned list too. Today's guest on All Things Photonics is a Sandia National Labs veteran and a bona fide expert on electromechanical radio frequency signal processing devices and technology, MEMS-enabled information processing, and, of course, quantum-integrated photonic circuit technology. Our discussion with Eichenfield being our podcast's maiden voyage into quantum-integrated photonics, today's episode provides the context needed to understand the significance of the technology. It also identifies drivers, recent progress, and challenges that remain in the field. As is true of related technologies and technology areas, concepts like scalability, material science, and cost-effectiveness take on roles of prominence in our discussion. The first thing to uncover is the link that exists between quantum, be it supercomputing or simulation, and photonic integration. Matthew Eichenfield with host Jake Saltzman is up next.
For the sake of this question, let's regard the disciplines of quantum and integrated photonics, those two realms, as separates, as independents. I want to ask, what has the proliferation of integrated photonics meant for quantum science? That's part one. And then part two of the question is the flip side. What opportunities in integrated photonics have recent advances in quantum opened up?
Taking it the first way, the proliferation of integrated photonics has really led to the possibility of having these ultra scalable quantum systems. So just to give you an example, so I'll struggle saying the name, the Zhujiang, I think that's maybe how it's pronounced, photonic quantum computer from USTC, from Jean-Wei Pan's group. So that is a 100-mode interferometer, and they formed this Gaussian boson sampling routine that outperforms, classical computing algorithms that can simulate the photodetection in that interferometer using squeeze light input. They, demonstrated I think pretty clearly quantum supremacy. But as these things move towards, more towards universal quantum computing, right? I mean, Gaussian boson sampling is in no way universal quantum computing, right? It's essentially a quantum simulator. It simulates the photon arrival of this very specific quantum machine. As people try to move towards really universal quantum computation, where you can, program an algorithm and have it compute something that's of utility to industry, science, society, you're going to need to scale those systems up. And in that paradigm, as a particular example, linear optical quantum computing, essentially, the number of interferometer elements will scale up as the number of modes in the system. So as you go from 100 modes in the interferometer to, say, 1,000 modes, you'll have 100 times the number of interferometer elements. So that scaling is pretty steep. It goes up like the square. And meanwhile, if you look at the demonstration, which was incredible, but I've never actually been to visit it in person, but just looking at the images from the paper, it looks like it's maybe approximately 2 meters by 2 meters, right? So that's like a 4 meter squared region of space to do this 100-mode interferometer. Okay, now in comparison, so we recently produced an 8x8, so an 8-mode interferometer on a chip for visible photons. And it's not even remotely as small as you could make these things. But that device, this 8-mode interferometer, was 8 millimeters by 3 millimeters, or about 24 millimeters squared. And if you were to scale that up to be a 100-mode interferometer, it would be about 4 thousandths of a meter squared. And so from 4 meters squared to 4 thousandths of a meter squared. It's 1,000x reduction in the area to make the same, number of modes in this quantum simulator, essentially. So there's an enormous reduction in the size. And that, means a few things, right? So one is just you can make more of them, right? So if you're limited in the total amount of space that you can use to make the system, being able to reduce the area by factors like that is a huge factor in being able to build larger and larger systems. I would say there are more profound things about it. Like there are things that you can't even do unless you have a very large number of modes in that system. Like if you ever wanted to do quantum error correction, it requires a lot of qubits because you end up essentially emulating a smaller number of logical qubits with a much larger number of physical qubits. And so the number of qubits you would need to make a really error-corrected, scalable quantum computer using photons like that is tremendous. And, there's just really no path by any other manufacturing means than the means that have been developed for making electronic integrated circuits to getting to those very, very large-scale systems where you can actually start to run, useful error-corrected quantum algorithms. So I think that's the impact that photonic integrated circuits are having on quantum science. And then, I think the impact that quantum science is having on photonic integrated circuits is that they're creating all these opportunities that we didn't even really, I would say as somebody who's been working in photonics for a while, there was not a lot of motivation or need from the scientific or commercial community to develop these kinds of photonic integrated circuits. A lot of them are very, very specialized. They're not the same circuits that you would use to do some kind of a optoelectronic interconnect between fiber and a computer in a data center, right? Those are going to be done using silicon photonics, using completely different wavelengths. They have a requirement for a huge bandwidth, right? Huge data rates. On the other hand, for a lot of these quantum applications, they require completely different wavelengths that are completely absorbed by silicon. You can't really use the same kind of techniques from silicon photonics. They don't have those same kinds of requirements for data rates, but they do have very strict requirements on loss and power consumption. So, if you're trying to use photons to do quantum computing, and the way that you turn light on and off causes a lot of loss, even when the sort of the system state is supposed to be as bright as it can be, as on as it can be, that essentially degrades the performance of your quantum computer. It means you'll have to have, more qubits to do error-corrected quantum computing, that the rate of, running successful computations will be lower. So it has a tremendous number of implications for quantum computing that are just sort of, they're not really commensurate with what's necessary for large-scale quantum computing. And so quantum science is creating all these new opportunities to create new kinds of photonic integrated circuits that use completely different materials and transduction mechanisms and, perform different kinds of functions. So I think they're really pretty synergistic in a lot of ways, and both fields are being driven forward, I think, much more rapidly by their sort of symbiotic relationship.
At what point for you did quantum and integrated photonics begin to overlap? Because you can certainly pursue quantum just in terms of electrodynamics or cybersecurity, certainly now, quantum cognition. You can attack quantum without stepping into photonics. And on the other side of that, of course, you can be an optics guy, and that's it. You don't go much further. At what point, though, for you did those two pursuits, I suppose, begin to intertwine?
In some regard, they intertwine really early. So my PhD was in, kind of creating some of the first devices where you could measure the quantum, states of mechanical motion using light. They're devices called optomechanical crystals. And so they were sort of, I specifically was seeking to create these kinds of systems along with my, my advisor and the rest of my research group that could prepare and read out quantum mechanical motion, not quantum mechanical, but quantum mechanical motion using light. And so very early on, that was kind of the theme of a lot of the work that I was doing. On the other hand, I would say that was more of a niche application, right? It really wasn't geared towards, computing per se, or networking or something like that. It was really kind of pursuing larger and larger scale demonstrations of quantum properties of mechanical objects, and elucidating new physics. So in terms of, quantum computing, quantum networking, and really the the crucial role that quantum integrated photonics play, that I think really started about maybe 8 or 9 years ago. I was approached by some people who were interested in quantum computing with various species of atoms. And one of the big challenges was that they needed a modulator technology that, might take like a trapped atom, a trapped neutral atom, or a trapped ion.
You say modulator technology. Would that be a component, or would that itself be, an area of science here? I'm just trying to clarify what that means, modulator technology.
Oh yeah, so that's what I'm trying to elucidate now. So for all these species of atom-like objects, that is like neutral atoms, ions, or vacancy centers, or donor defect complexes, things like that, all of them essentially require some form of optical control. So some set of levels in the system is either a qubit or is used to prepare quantum states of a qubit. And they require, typically visible wavelengths of light with sometimes pretty short modulation time. So that is like you need to essentially interrogate that atom-like object or atom with a very precise pulse of light, with a precise power and time dependence. And the state of the art there is really using acousto-optic technology. You can get these units that will take, one input beam and divide it up into, say 30 or so output beams. And then each one of those output beams can be individually modulated by an RF input. And those are using acoustic waves to essentially divide the beam up and then individually modulate the phase and intensity of those diffracted output beams. But it's pretty old technology, and there's some pretty big obstacles to scalable quantum computing with those. They're really big. So typical unit that could do the number of channels I just said, it'll consume tens of watts of power. They're kind of foot scale in dimension, the big units, and they cost a lot of money. They're very, very expensive to the point where if you wanted to build a realistic quantum computer with, say, trapped neutral atoms, the cost, even for just sort of scratching the surface for getting to, universal quantum computation or error-corrected quantum computation, the cost of just that modulator technology to be able to take a small number of laser beams, divide it up into channels that will individually address the atoms, and then control the power of the beams and the phase of the beams to do these quantum gates, just that part of the quantum computer will cost you something like, $10 or $20 million. And of course, 1,000 qubits is, like I said, just scratching the surface. So I was starting to get approached by various people who were interested in trying to build a more scalable, small form factor, inexpensive version of these, visible light modulators, essentially, that could satisfy the requirements of these quantum systems. And so I had been working in, photonics for a while, and then I'd also been working in some acoustic technologies that used aluminum nitride. And people had just started to use aluminum nitride as a modulator technology for light because it's electro-optic. But the issue is, even though aluminum nitride on paper looked like it would be a very good choice for these technologies, kind of like lithium niobate, it's an electro-optic material with a large band gap, so you can nominally, it can transport visible light with low loss. The issue is that in its sort of in the form that you can typically produce it on a wafer, it's polycrystalline. And so it actually ends up having a lot of just scattering losses. And as you go up shorter and shorter in wavelength, where most of these quantum bits would want to operate, interact with light, then that material gets lossier and lossier. And so at first we were trying to make, just better versions of that, really try to, squeeze all the juice out of the aluminum nitride lemon. And the reason for aluminum nitride, I should say, is because it's a CMOS compatible technology. So you can actually deposit it in a CMOS foundry. So it's one of these things where, I don't think people really appreciate the power of using CMOS compatible processing. If you have a 5G cell phone in your pocket, an iPhone, you've got something like 10 billion transistors in your pocket. And, forget about how big that chip is. I mean, the transistors are tiny, and that part's amazing too. But just the fact that there are 10 billion of anything in your pocket that was manufactured by man is crazy. Like, you will not encounter anything else in your life that is 10 billion of something that was made by man, right? I mean, pick basically anything. There's no thing where there were 10 billion manufactured things that you will ever come in contact with. And so this idea of scalability, people don't really understand how profound it is. If you can make a photonic integrated circuit in a CMOS compatible technology, then you can make it on 12-inch wafers in these fabrication facilities that will stamp out, your individual device all across a 12-inch wafer over and over and over again with super high yield. So almost everything on the chip will work, on this 12-inch wafer will work. You can make wafers in, 25 wafer batches at a time. You can make them 24 hours a day. It's roboticized, it's automated. So, the scale of the manufacturing for these, microelectronic circuits, when applied to photonics, it produces a level of scalability that just cannot be matched by anything else. Not even other micro technologies that just don't use the CMOS technologies. They even can't compare, because just the tools that are available are so specialized. CMOS, the material science is so advanced. But using these CMOS compatible technologies like aluminum nitride was our real goal, so that we can make them ultra scalable. And again, like I was sort of alluding to, it didn't really work out because of the scattering losses in aluminum nitride. So what we did instead was we started to use aluminum nitride, which is also a piezoelectric material. We started using it as an actuator. So it produces strain in the photonic integrated circuits. And then that strain transfers to the waveguiding layers like silicon nitride or silicon dioxide or aluminum oxide. And through something called the photoelastic effect and the optomechanical moving boundary effect, you can produce a change in the speed of light in the waveguide materials by applying strain through this, integrated aluminum nitride strain actuator. And so that allows us to change the speed of light in the circuits dynamically, by applying voltages, and we can ultimately turn that into phase and amplitude modulation, frequency modulation, polarization modulation. So we had developed this kind of platform, demonstrated this platform for making ultra scalable visible wavelength modulators in this CMOS compatible process. We were making them in Sandia's foundry, which is itself a volume CMOS foundry, low volume in comparison to like a commercial CMOS foundry, but it is certainly capable of high volume CMOS fabrication. And so then all of a sudden, once that was built, we started getting calls from lots of people. And one of the people in particular you've had on the podcast, Dirk England, he contacted me very early on. He was incredibly interested in using that technology to scale up some really cool stuff he'd been developing, using diamond microchiplets to host these vacancy centers in diamond that can behave like atoms, but you don't have to trap them or anything. They're just trapped inside the diamond. So he had developed techniques for making little kind of diamond microchips that you could pick up off the diamond wafer and place onto other photonic integrated circuits. So you can kind of think of it like a specialty quantum photonics chiplet that you could mount into a more scalable circuit that can take those photons that are, say, emitted by the diamond atom-like emitters and route them through specialty circuits that cause them to be become entangled with each other, to turn channels on and off, to distribute them across the chip, to route them to detectors, all those kinds of functions that you need to actually make a quantum computer. And so he contacted me to start to collaborate on making these scalable photonic integrated circuits. We ultimately got involved with the MITRE Corporation, and the PI there is Jerry Gilbert. And we've been working on this quantum moonshot program, trying to develop these kinds of ultra scalable photonic integrated circuits now for, I think, about 4 years. And so that's been a really huge collaboration. There are, I think, something like 30 kind of permanent scientists between MIT, MITRE, Sandia, and U of A working on that. And that I think is really pushing the boundaries of what we can do with quantum photonic integrated circuits. So that's been kind of the story for me for this quantum photonics, I think.
You mentioned a couple of times in your first response commercial or commercialization, and certainly in quantum, I don't mean to say low level, but we've seen things like the CSAC, for example, or atomic clocks. Like these are commercial items. How do you position this notion of commercial in your work? I mean, is that sort of the ideal, optimal end game for an avenue of research, or is there sort of interest in the research itself for you?
I'm not interested in commercial in the sense of making money. I'm interested in the commercializability because I want this technology to be disseminated so that it can impact the world. I mean, there are quantum algorithms that optimize the traveling salesman problem, exponentially faster than any power of classical computing, right? So the traveling salesman problem is, essentially the problem of logistics, right? How do you optimally, have a set of resources travel along complex paths with complex optimization problems, say like an airline, right? If you're an airline, how do you optimally configure your airline schedule so that you can send the planes on the smallest number of trips, carrying the most number of passengers, using the least amount of fuel, making sure that you still serve small markets and yada, yada, yada. I mean, I'm obviously no expert in commercial airline scheduling, but those kinds of problems and any smaller system that just requires logistics, trucking and distribution, worldwide shipping, every logistics problem essentially involves the traveling salesman problem, and that's just one example of a problem that is classically hard and scales much more favorably with a quantum algorithm. So the impact that you can have on society, making the distribution of all the world's goods and services more efficient, inexpensive, that's huge. You can make it, less expensive to distribute things to places in the world that are impoverished. You can increase the speed at which you can distribute goods, right? I mean, we've all seen now basically how fragile some of the infrastructure is for distribution. During the pandemic, distribution was disrupted, and it didn't take much to essentially cause the whole system to come crashing down and have, ships in shipyards just, sitting offshore with, millions of dollars worth of goods that couldn't even be distributed because there was not even a direct disruption in shipping. So I think all of those things, they just have such a big impact on society, and they need to be done, right? We need to get these things done to make the world a better place, basically. So, if you just keep things in the laboratory with scientists, I mean, you can do a lot of amazing things, but you're never going to have the kind of reach and impact that you do, if the technologies are ultimately commercialized. So for me, that's the big motivation.
I want to talk about your paper in Nature Electronics, your team's paper, Nature Electronics, earlier this year. It outlines an approach to fabricate all acoustic radio frequency signal processing front ends on a chip. We talk a lot about integrated optics. We talk a lot about silicon photonics. We don't pay anywhere close to equal attention to the acousto-electric effect. Can you give us a crash course in the effect and I guess more to the point, what it means, what it can offer radio frequency electronic systems?
Yeah, let me start with the motivation here. So if you were to pull out, your cell phone and break it apart, you'd be surprised to find inside that there are something like, if you have a 5G cell phone, you probably have something like 50 or more chips in your cell phone that convert radio waves to sound waves and back. And most people are shocked when they hear that, right? I mean, I don't think anybody that's walking around with cell phones, no reasonable fraction of people realize that the radio waves are being converted to sound waves and back. And the reason that they're doing that is because, we all share basically the same radio waves, right? I mean, if there are 100 people in a room, every single one of them is sharing the same space in terms of the location that the radio waves are occupying, right? The way that they're distinguished from each other is largely due to the frequencies that they're using. And that occurs in a bunch of different ways, using slightly different frequencies to talk to different phones and encoding things in frequency. But another big one is just the fact that when your cell phone is broadcasting to talk to a radio transmitter, to talk to a base station where it'll be relayed, it's broadcasting with something like a watt of power. And the receiver circuitry is super sensitive. It can receive something like a picowatt of power and still, be able to pick up the signal. And so, there's this huge disparity in the size of signals that your phone is sending and the sizes of signals that your phone is receiving. And because of that, it's actually would be very easy to completely overload the receiver circuitry using the transmitter. So they have to separate them in frequency. And you can't just arbitrarily separate them in frequency, because you have to use the same antenna, right? So you have one antenna that's going to use this particular radio band, and within that antenna bandwidth, you need to be able to send really powerful signals and receive really weak signals, and those have to be separated in frequency. And so the thing that does that is this acoustic filter technology. There are a couple main types. One is called surface acoustic waves, and the other called bulk acoustic waves. But they're both devices that turn radio waves into sound waves at the same frequency and back. And in the domain when they're sound waves, they basically get filtered by this resonator, this acoustic resonator, and then they turn back into radio waves, and it goes along out into the circuit. The rest of the things that have to happen are to basically turn the encoded data on the radio wave into data on your cell phone. They have to be amplified. They have to be what's called mixed. So that means converting frequencies. They have to be mixed with oscillators that are sometimes produced with acoustic resonators. But like there are a few chips that have to be made with acoustic resonators. Those are the filter chips. And then typically everything else is made with transistor-based technology. So all the amplifiers and the mixers, those are all done with transistors. What that means is that when you put together a system to make a radio, and by a radio, I mean the thing that sits between the radio front end is the thing that sits between the antenna and the computer processor, basically. And so it has to take data, put it on radio waves and send it out, and it has to receive radio waves with data on them and turn them into data. And that is all done with these mixed technology circuits that use these piezoelectric acoustic technologies to turn radio waves into sound waves and back, and then these transistor-based technologies to do all the other stuff. So people have been trying for a long time to produce those filters in the transistor-based technologies, but it's really not possible. Even if you could reproduce the performance, you would have to use a lot of power to do it because they'd be transistor-based devices. The piezoelectric acoustic devices are completely passive, and it just turns out that you really can't emulate the performance anyway with these transistor-based technologies. And so the motivation for this is to kind of flip this on its head, right? Like, what if we could not emulate all of the acoustic functionalities in the transistors, but go the other way? What if we could emulate the transistor stuff in the acoustic domain? So that is, we'd have to make amplifiers, we'd have to make mixers, frequency converting devices, and we'd probably have to make, oscillators and switches and a few other things. So it turns out there was all this really amazing work done in the late 60s and early 70s where people were trying to develop something that looked like an acoustic wave amplifier for just this purpose or similar purposes. And they were doing it before they really had invented things like molecular beam epitaxy and other kinds of really precise epitaxial material deposition techniques. So the best they could do was kind of, like evaporate a semiconductor film on top of a piezoelectric film. And then the semiconductor would, even though it was really kind of terrible semiconductor material, would house some some electrons, and they could flow the electrons in the direction of the acoustic wave. So you launch an acoustic wave, you apply a voltage that accelerates the electrons so that they're traveling in the same direction and faster than the acoustic wave. And if you can satisfy that, then the electrons will give their energy to the acoustic waves. They'll amplify the acoustic waves. And so I had been, looking at these papers and thinking, I think it's been 50 years basically since this work was done, or maybe at that time 45 years. And I assumed that there would be some better way to solve the problems now. And so I started working on that. And we have really rapidly, my group at Sandia, and now starting with the group at U of A as well. And I need to give a lot of credit to a few other people that were really instrumental in the development of this work. Those are Tom Friedman, Anna Tauchi-Pedretti, and Lisa Hackett. But that team, we really put together a system and developed it to the point where now we can we're making amplifiers for sound waves that are as good as the microwave amplifiers are for microwaves. So if you buy a microwave amplifier, a pretty good one, it has say 30 dB of gain and has what's called a noise figure of around, say 2 or 3 dB. And let's say frequencies around a gigahertz or something like that, right? So we actually just published this paper in Nature Electronics where we made an acoustic amplifier that has 30 dB gain, a 2.8 dB noise figure, and operates at a gigahertz. And it also has low power consumption. And so we made this amplifier. We worked together with Donna Weinstein's group at Purdue to use the same kinds of techniques to make an acoustic switch. We have results coming out soon where we've demonstrated an acoustic mixer. And so we're really knocking off all the all the cans off the wall to say, like, yes, we can absolutely make all these technologies in the acoustic domain that we thought could only be done in transistor-based technologies. And so now all of a sudden you can imagine having a single chip that's very small that has all of the functionalities that you need to make a whole radio frequency front end. And that will allow the systems to be shrunk by something like 100x. And so systems that really are too small to accommodate powerful wireless technology, they might be able to finally take advantage of it. And systems that already have wireless technologies in them can have a lot more bandwidth and functionality. You can make them smaller and lighter. So that's really the big motivation there. And like I said, I mean, essentially every wireless device that has reasonably high performance has these acoustic filters inside, and can thus be, potentially highly miniaturized, by using these acousto-electric interactions between semiconductors and acoustic waves.
I want to talk about the MEMS-enabled quantum systems group at Sandia. Certainly you know it well. The formation of this group, the establishment of this group, occurred right around what many in the photonics industry would phrase as the MEMS revolution. Might also call it the MOEMS revolution. At what point was it evident to you that it was sufficient, MEMS technology was sufficient, to build a working group around?
I don't know that I ever had that realization in an active way. I should say, too, that MEMS-enabled Quantum Systems Group at Sandia is really just the name that I gave to a subset of a department, which is really the MEMS Technologies Department. So Keith Ortiz is the manager, has been ever since I started at Sandia. And Keith has done a really amazing job of hiring really creative people. So when I started there was a guy in particular named Troy Olson, who's now a professor at Pennsylvania University, or University of Pennsylvania. And Troy was really kind of my mentor at Sandia when I first started. So he had developed this technology for making aluminum nitride resonators for filtering technologies, again, for these wireless systems. And I was really interested in those things because it was pretty clear looking from the outside in as sort of a photonics person that a lot of MEMS technologies were really understood in the language of circuits, right? So thinking about things in terms of the equivalent electrical circuits that they produce. And I immediately started to see a lot of potential for understanding things in terms of really waves, right? And the kinds of things that we do in integrated photonics and just, even bulk photonics, that they just really hadn't been sort of taken advantage of yet. And so I started working in sort of the pure RF technologies, really learning from Troy. And then at some point I got really interested in the idea of, so then I understood how to generate, acoustic waves and detect acoustic waves, using these piezoelectric technologies in MEMS. And at the same time, my PhD was in generating and detecting acoustic waves using light. And so it became pretty obvious that there would be this connection between optomechanical science and technology and MEMS, RF MEMS in particular, science and technology. And so at that point, I think it sort of carved its own niche, right? If you have the expertise in both sides of that coin, then you can do things that aren't possible with one or the other, right? I mean, if you're just doing MEMS, you can sort of think a little bit about how to interact with light, but a lot of people, what they were doing was more sort of bouncing lasers off of MEMS devices and things like that, and there really wasn't a lot of integration of MEMS in the, from the other direction. People that were doing nano-optomechanics, there were only a small number of them were really starting to use MEMS, things like surface acoustic waves. And I think Hong Tang at Yale deserves a lot of credit for integrating aluminum nitride into, photonics at first in the beginning, just to make it, to use it as an electro-optic material, but ultimately using them to generate and detect phonons as well. So there were a lot of people Peter Rakich, also at Sandia, should probably be in that list of people who are really interested in using MEMS technologies to combine them with nano-optomechanics to make more powerful versions of either one. So there's a lot of overlap between these fields. And so this is a really long answer to your question, but I think like I said, there was never a point where I was sort of actively thinking like this should be a whole field. It was just as you sort of progress in your skill sets and you start to realize there are all these niches you could fill, then there are just more and more of them, and they start to cascade. And then before you know it, there are sort of 20 or 30 people actively working with you to make these really cool technologies become a reality. And that's kind of how it all happened.
As I speak with you, you've been here in your new locale in Arizona for all of 18 hours, and then that has to do with your role as an educator. And this is a question that takes us really to a grassroots level, an increasingly grassroots level. There's increasing attention both here in the U.S. and around the world in the cultivation of a quantum workforce, and I know that may fall somewhere outside of the core of your scope. Curious to get your thoughts on first that need. And second, the steps that the entirety of the optics and photonics community can take to fill that need.
Yeah, I mean, first of all, I have to say, like, it's definitely not outside of my main scope anymore, right? I mean, one of the reasons I wanted to, I should clarify for the audience, right? So last August, I formally resigned as a distinguished member of the technical staff at Sandia and started as an associate professor at University of Arizona. I have a joint appointment between Sandia and University of Arizona. So my main employer is now University of Arizona. I'm a tenured professor there, but Sandia still essentially funds University of Arizona to have me work on Sandia projects to provide my expertise in service of the national interest and that sort of thing. So I have this dual role, but one of the reasons I wanted to do it in the first place was because I was really passionate about educating this workforce you're talking about, this quantum workforce. And University of Arizona is really taking that very seriously. So there's the dean, Tom Koch, and Professor Saikat Guha and others are creating all kinds of new initiatives for quantum education in the workforce. We actually have a new QISE, so Quantum Information Science and Engineering Master's program that's even available remotely to students. So students are taking my class now, which is in quantum integrated photonics, from all over the country, and if I think about it, maybe all over the world. So I am really involved in that and trying to get more involved and passionate about it. And what I think is the importance for doing it and the impact to society is that these are really challenging systems that require both people at the top down kind of driving what these new systems are going to be and developing, even new systems that we haven't thought of yet. And a lot of that will come out of academia. But if we really want to have broad reach and impact for quantum science, like I've been talking about, we need a skilled workforce in the United States and the world, but particularly in the United States, that can actually build and work on these systems. They're incredibly complex. There's not a single qubit system you can point at that's simple, right? I mean, superconducting circuit qubits, they require these ultra high precision superconducting materials to be built into electronic circuits. They live inside of dilution refrigerators, which are keep materials at some of the coldest temperatures ever demonstrated. And that's where they have to live to operate. They use a lot of complex microwave engineering and classical electronic circuits to control the quantum computer. And it's the same with all of the photonics-based quantum systems like trapped neutral atoms, trapped ions, quantum computing with vacancy centers in materials like diamond. They all are super sophisticated. And there's a huge range. Like I said, it's not just these, that you need these academic scientists to be working on these things. You need a lot of people, really talented mechanical engineers and electrical engineers and optical engineers to design the systems that actually make these things work at scale. And it's going to be really important to develop the workforce as these technologies come online, because if we wait to do it, then we'll have all this potential for making quantum science, kind of have its ultimate impact on society, but we won't actually be able to realize it because we won't be able to produce enough of the systems, or we'll just be outcompeted by, other countries who are investing in these quantum workforces. So I think it's really important for the U.S. and the world to really take seriously the development of quantum education. It sounds kind of out there, right? But this is part of the next technological revolution. Quantum science and things like kind of tailored biological medicine. I mean, these are all new revolutions that are taking place before our eyes, and we have to invest in them in ways that that we invested in things like silicon microelectronics in the 60s and 70s, if we really want to see them benefit society in the same way that microelectronics has.
That concludes this week's episode of All Things Photonics. Thank you to our engineer, Alan Shepard, and to our news editor, Jake Saltzman, as well as to this week's sponsors. Our featured music is courtesy of betterwithmusic.com. Most of all, thank you, our listeners. As always, you can share your thoughts, pitch us ideas, and let us know how we're doing. You can reach us at allthings@photonics.com. All Things Photonics is available on all major platforms, including Spotify, Apple Podcasts, as well as on our website, photonics.com.